Hello guys, today we are going to discuss about compound vapor compression refrigeration system. So all the first, what is compound compression? For this we using two or more compressor in series to compress low compressor refrigerant to getting a high compression ratio. Okay, for this we use the compressor in series. Okay, maybe the two or three. So all the first when we getting refrigerant from the evaporator, we compressed in first compressor, and after that we compressed using the second compressor. So we have in the series the first, after then the second, after then the third, to getting a higher compression ratio. Okay, we know very well that if we can decrease the compression work, if we can decrease the compressor work, then we can increase coefficient of performance of a refrigeration system. We can reduce the compression work if the refrigerant is compressed very close to saturation vapor line, and can be achieved by compressing the refrigerant in more stages, like using 2 or 3 or more compressor in the series. Actually, we want to increase the efficiency of COP of refrigeration system. So if we getting the less compression work, then we can increase coefficient of performance. And the second, if we can increase the refrigeration effect, then we can increase the COP, because the COP is refrigeration effect upon work done. So now in the first stage we are trying to decrease compression work using the two compressor in the series. So we can reduce compressor work to getting a same compression ratio and a same temperature effect. Okay, if we use the a single stage compression, then we need more compression work to getting a same compression ratio. But if we use the two compressor in the series, then we can get same compression ratio with the minimum compression work. Okay, so for this, all the first, consider a two-stage compression. Okay, in this we using the two compressor 1 and the compressor 2, with liquid intercooler, or also called a flash intercooler. Okay, in this we use a flash chamber with the liquid. Okay, so this is the diagram of two-stage vapor compression cycle with liquid intercooler. Okay, so in this we have compressor which used to compress the liquid in the first stage. After exit to evaporation, after exit to evaporator, it entered at a point 1, and after the compression with the low pressure compressor, it is known as a low pressure compressor compared to the second compressor, because in the second compressor we getting a high pressure. Okay, so the first compressor is known as a low pressure compressor and the second is known as a high pressure compressor. So the after exit to evaporator, refrigerant entered at a point 1, okay, at the suction of the compression, and after the compression discharge to point 2. Okay, at the discharge point 2, then it passed through a intercooler. Why we use the intercooler? Intercooler we use to decrease the temperature of superheat refrigerant. After the compression from the first stage, we getting a superheat refrigerant. Okay, so we can't use in the second compressor. Okay, superheated refrigerant we can't use for the further compression. So decrease the temperature of it. Okay, so using this liquid flash chamber, we can decrease the temperature of superheat. So after then passing through this flash chamber or this liquid intercooler, we getting dry saturated refrigerant. If we know very well that we can increase the COP of refrigeration if we compressed a refrigerant nearest to the saturation vapor line. Okay, if the compression work is very close to the saturated vapor line, then we can increase COP of the refrigeration, because we can reduce compressor work. So then the superheat vapor which comes from the compressor with the mass M1. Okay, assume that after exit to evaporator we getting the M1 mass of the refrigerant, okay, which compressed in the compressor in the first stage, and then it is the comes in the intercooler. Okay, in the intercooler we have liquid refrigerant. When a high temperature vapor comes contact with the liquid, okay, then the temperature of this superheated refrigerant is decreases and it is converted into dry saturated. At the same time, the few amount of liquid refrigerant which is available in flash chamber has vaporized. The few amount of this is vaporized and it is the mix with the mass M1. Now the total mass is known as a mass M2, because the M1 we getting from the compressor and the M3 the few mass of the liquid refrigerant which convert into the vapor due to absorbing the temperature from the superheated vapor. So the total mass which exit from the intercooler is M1 plus M3, so it is known as a M2. Now that this mass is passed through the compressor in the second stage and it compresses isentropically from 3 to 4. Now after exit to compressor we need to superheating process. Okay, so after then it passed through condensation process. Okay, condenser. After desuperheating we getting dry saturated refrigerant, okay, which pass through the condenser. In this the phase of the refrigerant is changed and we getting saturated liquid at the point 5. Now the M2 mass is exit from the condenser. Now the few mass of the M2 which again expand in the expansion valve, first or also known as a float valve, because this valve we used to make up a amount of refrigerant which convert into vapor. Okay, so we need the equal to this amount. Okay, suppose the M1 is vaporized during the desuperheating process in first stage, so we need the M3 mass to make up the refrigerant. So we have a constant level of the liquid refrigerant in flash chamber. Okay, now the remaining mass, so the remaining mass is M2 minus M3. So the M2 minus M3 is equal to M1. So the remaining mass M1 is passed through the expansion valve. This is process 5 to 7. Okay, and after then it passed through the evaporation and we getting refrigeration effect. So this is the entire cycle of two stage vapor compression refrigeration system with a liquid intercooler. Now because the few amount of the refrigerant which mixed with the M1 is again the makeup by this wall V1, so we have a constant mass flow rate through the wall 2. Always we have constant flow rate through this expansion wall 2. Now this is the PH diagram, not the T, it is the PH diagram, okay, not the T. Okay, just correct it. This is the sorry, it is H. Okay, so now this is corrected. Now pH diagram. Okay, in the pH diagram the point 1 to 2 is indicate the compression. Okay, in this process 1 to 2 refrigerant compressed. Okay, this is the process 1 to 2. Okay, in the 1 to 2 the mass M1 is compressed by compressor isentropically. Okay, and we getting new pressure range the P2. That means after the compression we getting the pressure P2. Okay, P1 we have evaporation pressure. Okay, so the compressed by compressor P1 to P2. Okay, and we getting the same temperature T1 to T2. Now in this, during the compression work, we can write as a m1 into m1 is the mass, and the enthalpy difference is, energy difference is H2 minus H1. So the total work done by this compressor is m1 into H2 minus H1. Now process 2 to 3. Process 2 to 3 we use for the intercooling purpose, okay, for the desuperheating process. It is a desuperheating process. We decreasing the temperature of superheated refrigerant. So we getting a dry saturated. Now dry saturated vapor again compressed in the second compressor. Okay, now we have mass m2. We discussed earlier that we getting in the second compressor we have the total mass m2. Okay, m1 plus m3. The few amount of the refrigeration is getting from flash chamber. Okay, so the m2 is compressed isentropically from the process 3 to 4. Okay, so this is the work of second compressor. Okay, so the work done by the second compressor is m2 into H2 minus H3. Okay, sorry, H4 minus H3. So this is the work by second compressor, H4 minus H3. Now the process 4 to 4 days is desuperheating process. Now at the 4 days we getting dry saturated vapor refrigerant. Now this vapor refrigerant is passed through the condenser. The latent heat rejected to atmosphere, and at the point we getting the phase has changed, and now we getting a liquid saturated refrigerant. So the process 4 days to 5 is condensing process. In this, heat is rejected to the surrounding. 5 to 6 process. In the 5 to 6 process, at this process we using the expansion valve 1, okay, for the makeup purpose, okay, and also known as the float valve. So this is the process supplied to makeup refrigerant into flash chamber. Okay, so we can maintain a particular level of the refrigerant. Okay, so to maintain a constant level of liquid refrigerant in the flash chamber or intercooler. Okay, so this is the throttling process 5 to 6. Okay, throttling process 5 to 6. Okay, this is line. The point 5 to 6 is the throttling process for this valve. Now process 5 to 7. Process 5 to 7. The process 5 to 7. Process 5 to 7 we use for expansion process. Okay, now the liquid saturated vapor expand in the expansion valve. Okay, so the pressure is decreases from the condensing pressure to evaporation pressure. Okay, it is the indicate by the point 5 to 7. Okay, 5 to 7 is expansion process. Now 7 to 1. Okay, process 7 to 1. 7 to 1 is the latent heat during this process is absorbed by liquid refrigerant, okay, in the evaporator using the blower. Okay, so the latent heat is absorbed by the refrigerant, and the refrigerant is converted into vapor and exit to evaporator, and this vapor refrigerant is absorbed by the compression for the second cycle. So during this process 7 to 1, the refrigeration effect is because the M1 is absorbed the latent heat. Okay, latent heat of the room is absorbed and vaporized. Okay, so the total refrigeration effect is M1 into energy difference. So it is H1 minus HF7. H1 minus HF7, and also the HF7 is, or the H7 is equal to HF5. Okay, so this is the entire process of this cycle, and after that we can calculate. After this we can calculate the COP of the refrigeration system. Okay, so all the process is clearly defined in these notes. Okay, the process 1 to 2, process 2 to 3, process 3 to 4, process 4 to 5. Okay, 4 days to 5, because the 4 to 4 days is D superheating, 5 to 6 and the 6 to 7 and 7 to 1. All the process is clearly mentioned in this. Okay, this process is the 5 to 7 process. Okay, not the 6 to 7, this is the 5 to 7 process. So the all things is clearly mentioned in this. Now how to get the COP? Okay, we know that the total compressor, okay, total work due to the compressor is the work done by the first compressor plus work done by the second compressor. So total work done is the equation number 5. Okay, total work done is the M1 into H2 plus H1, sorry, H2 minus H1, not the H2 plus H1. This is the, so total work done is M1 H2 minus H1 plus M2 H4 minus H3. Now the COP is refrigeration effect upon work done, and the refrigeration effect is H1 minus HF5. Okay, this is the refrigeration effect. Okay, M1 into H1 minus S7, and S7 is equal to HF5. Okay, so it is M1 H1 plus H1 minus HF5 upon the total work done by the compressor. Now we know that the M2 is equal to M1 plus M3. So using this equation, okay, or the energy balance equation at the line P2 is equal to P3, okay, at this line, okay, applying the energy balance equation between the point 6, 3 and the 2, okay, in this line we can getting energy balance equation is M1 H2, okay, plus M3 S6 is equal to M2 S3, because the M1 plus M3 is equal to M2. Now using this relation, after then putting the value of the M2, we can get the value of the M3, the mass, the amount of the mass which mix with the M1 or the same amount which make up after the condensing process. Okay, so this is the M3. So using this relation we can calculate the value of the M3. Now the mass taken by intercooler and the mass given by intercooler, using this relation, the mass which entered in this. Okay, so from this equation, M1 is entered, okay, M2 is given by this, M1 is entered by the compressor, and the M3 is entered by this. So the M1 is entered, so the M1 is taken by this, so the M1 is taken and the M3 is also taken by the intercooler, and the M2 is given by this intercooler. Okay, so the using this relation, okay, so the how much the heat is given by this M1 into H2, okay, M1 into H2, because this point is the 2, so the M1 into H2, so this is M1 H2, sorry, okay, the value of this entered is M1 H2. Okay, so the M1 H2 is energy is entered in the heat exchanger in intercooler, and the energy which exit given by this is M2. So the M2, the energy level is the H3, so M2 H3 is given by this. Okay, this is the given, and the taken by this float wall is M3, and the energy value is this H6. Okay, so the M3 H6 is taken by intercooler. So the total energy which taken by this and the energy by given this is this plus this is this plus this is taken by the intercooler, and this amount is given by intercooler. Okay, so using this relation, we can calculate the second mass M2. Okay, so the M2 is we can calculate using this relation. So clearly mentioned in this, we can calculate the value of M2. Okay, this is the value of M2 and this is the value of M3. Using this relation we can calculate the all things which we need. Okay, now what is the difference and how it is the differ from the single compressor? Okay, we know that we trying to decrease the compression work, but it is the happen or the not, or it is the decreased or not, then how to compare? Okay, so okay, in this diagram, okay, see clearly to this. Okay, in this the work done by the first compressor is this, okay, from the this to this, and the work by the second compressor is from the this to this. Okay, suppose this is the at the 4 we have the temperature is T4. Okay, at the point we have the temperature T4. So in the single stage during the using the single compressor, okay, if you want to obtain the T4, okay, if you want to obtain the T4, okay, higher compression ratio, okay, then the compressor take place according to this. Okay, compressor take place according to this. Okay, this situation if we using the single, okay, during single stage compression. Okay, so we getting compression like this. Okay, like this. Okay, so we need to do a high work during the compression, because at this point we getting the value of the H at this. So the total compression is, or the total work done by the compressor is equal to this. But during the two stage we done the compression work between these. Okay, so it is the clearly we can see that the compressor work is decreases if we using the two-stage compression, and we can get a higher compression ratio. Okay, it is same temperature or the high temperature from these using these two compression. Okay, so this is the sufficient for today. Thank you so much.